so I'm going to do two more examples of area enclosed by two functions. So again, remember this is exactly the same as the area between two functions. The only additional part is you have to figure out where they're equal to each other. So because they intersect, that's the endpoints. That's your a and your b, and then which function's bigger than the other function. All right, so I've got two functions here. Again, I've got a parabola and a line, and you can do it algebraically or by hand again, as long as you show me. If you're solving it algebraically, make sure you show me algebraically. If you're solving it graphically, make sure you show me the picture and how you got your answers. All right, so show me the definite integral with correct notation, and then, if you're solving algebraically, show me the algebra. If you're solving graphically, show me the graph. All right, so I've got my function g of x, which is our parabola. I've got my function f of x, which is my line, negative 5x plus 28. I'm going to solve it algebraically, but like I said, I'm going to solve the first one algebraically, maybe I'll solve the second one graphically. All right, so I'll do one of each. So first example I'll do with algebra, second example I'll do graphically. All right, so with algebra, the first step is to find where my functions are equal to each other, right? Because it's completely enclosed. The endpoints are where they intersect. So my f of x is negative 5x plus 28. My g of x is negative x squared plus 10x minus 8. Now, I know I'm going to solve this by factoring. I don't like negatives on my square term, so I'm actually going to move my quadratic over to the other side, meaning I'm going to add my x squared. I'm going to subtract my 10x. I'm going to add my 8. That's going to leave me with 0 on that side. These are all gone, so I'm left with 0 over here. And then x squared minus 15x plus 36. Solve it by factoring. Factors of 36. When I add them up, I get negative 15. So negative 12 and negative 3, right? Take negative 12 times negative 3. I get 36. Negative 3 plus 12 gives me 15. And so my endpoints are 12 and 3. All right, those are my endpoints, meaning the area is over the interval 3 to 12, right? 3 is my starting point, 12 is my stopping point. So the area is completely enclosed by my two functions between point 3 to point 12. And if you graphed it, so you could graph it and find the points of intersection, which, like I said, I'll do that in the second example. All right, I know the area is over that, so that's where I'm going to integrate. I'm going to integrate between 3 and 12. Now, the next step is I have to figure out, well, which function's bigger, right? Which is the bigger function. Since I'm solving this by hand, I'm going to pick a test point. So a number between 3 and 12, 5, right? So suppose I pick 5. I kind of like 5s. So I'm going to take 5, plug it in my function f. I'm going to take 5 and plug it in my function g. All right, so again, I'm taking 5 and I'm plugging it back into these original functions. So when I plug 5 into my function f of x, I'm going to get negative 25 plus 28, so that comes out 3, and then g, I'm going to actually plug into the calculator, so negative 25 comes out 17. All right, which means g is bigger. Right? G is greater than f. All right, so when we integrate, when I find my integration from 3 to 12, I'm going to take g of x and subtract away f of x. If I do it the other way around, I'll get a negative number, and I don't want negative numbers. All right, so my area is equal to the integration of 3 to 12, taking my function g of x, which g of x was the negative x squared, plus 10x minus 8, subtract away the f of x, which was negative 5x plus 28. And if you can simplify, I want to see at least this, but I did say simplify. All right. So subtract accordingly and collect like terms, which would mean the simplification step. So I get negative x squared plus 10x minus 8 plus a 5x minus 28. Collect your like terms. And so the area is equal to the definite integration from 3 to 12 of my negative x squared plus 15x minus 36 with respect to x. So again, I want to see at least these two expressions. And then you can solve the area graphically. So remember, when you solve this graphically, you're going to plug this into the calculator, negative x squared plus 15x minus 36. All right, so we graph that. make sure your window's big enough. A standard window won't work because I have to go out to 12. And so I'd probably go from, I'd change my my X maximum to probably 15 just so that I can see the picture. Alright, which comes out to a parabola like this. This is 3, this is 12. And then shade that area in. That area equals the definite integral. So again, that's what this shaded region equals. And it comes out positive. It comes out 121.5 is the area between or enclosed by. F of x and g of x. Alright, so area completely surrounded by those two functions. So that's by hand, other than I didn't solve my integration by hand. You could solve it by hand. You'd find the general antiderivative, plug 12 in, plug 3 in, and subtract. Fine. Alright, so area between two curves by hand. My second example, I'm going to solve it on the calculator. Alright, so I'll plug these into the calculator. Alright, so solving graphically. Meaning I'm going to do all the algebra graphically. So I'm going to graph this in my calculator, and I'm going to graph this in my calculator. So I'm going to pop up my calculator. I'm going to clear out what I have in here. So I'm going to plug in my first function, which was f of x. So that was x squared plus 8x minus 10. Which I probably will have to make my window a little bigger, but I'll start out with a standard window and adjust from there. Negative x squared plus 10x plus 14 was my second one. Double check and make sure I've done those right. X squared plus 8x minus 10, negative x squared plus 10x plus 14. And I can see here, so if I go ahead and hit graph, I know that my picture is going to be off my page. So I'm going to have to make my window bigger. So I'm going to go to window. And I can kind of look at my table, actually. If I go to my table's kind of listed here. It kind of gives away, my numbers are fairly large. Looks like they're up in the 20s and 30s. So if I look here at my table, and so I'm going to use my window to do that. So my window, I might leave my x values 10 and negative 10. But my y values, I might make negative 50 and positive 50. Just to be on the safe side, I'll just scale by 5. See if that gives me... Alright, so that works out perfect. So there's my first function, and there's my second function. So the first function was f of x, so the blue function is f of x. The red function is g of x. So there's the area I'm looking for. So the first thing I have to find is where they intersect, and I can do this on the calculator. Instead of by hand like I did in the last example, you can do this on the calculator. You hit second trace. If you see number 5 there is intersect, so I select 5. And then it asks you first curve, second curve. And so what you do is you get as close as you can to the intersect moment on your first curve. So my first curve is the blue function. And then the second curve, now I'm on the red function, which, it looks good enough. I don't have to move it. And then my guess, I'm going to just leave it. So as long as the moment's close. Alright, so they intersect at the first moment, negative 3, negative 25. File that away, negative 3, negative 25. Alright, now I'm going to find the second intersection, so do the same process, second trace, 5, first curve, second curve, guess, so I've got to go all the way up to the other spot. Again, as long as the number's close, I just usually hit my button 3 times. You have to hit it 3 times, right? First curve, second curve, guess. And so this moment intersects at 4:38. Alright, so there's the area completely enclosed, so now, again, I've done the work on the calculator. Now I've got to show the reader, ergo your teacher, that that's what I did. And so when you go show your work, if you're solving it graphically, show the picture. Alright? And so my first curve, which I'm going to draw blue, right, that was my f of x. And then I'm going to go to red. I'm going to go ahead and kind of mark off my points and make sure I got them. My red curve is g of x. I found this point on my calculator. This was the point 4:38. I found this point on my calculator, which was the point negative 3, negative 25. All right, this is where they intersect. right? And show the picture. This is how I know this is what you did to solve it. And so the area I'm looking for is this area, right? And so remember, the second step was, well, which function's bigger, right? So first step, figure out, well, f of x equals g of x, they intersect, at x equals -3 and x equals +4, right? That's the moments where they intersect. That's where my area is between -3 and +4, right? It's the x values, not the y values. X values between x -3, x +4. All right, so when I want to find my area, it's over the integral -3 to 4. All right, then my next thing is, well, which one's bigger? Well, the red function is bigger than the blue function over that region, right? It's above. The red function is the g of x, right? G of x is larger than f of x. So based on the graph, g of x is larger than f of x based on the, all right, see the graph. All right, that's the work. That's why you need to show the graph so that we can see, aha, yeah, that's true. If I look at the graph, we've labeled the red function's the g of x, the blue function's f of x. The reader can see that, okay, that's true. All right, your logic is true. And so my area equals the integration from -3 to 4 of g of x minus f of x. All right, and then you solve. All right, and I want to see this area function. -3 to 4 g of x, which was my x squared, negative x squared, plus 10x plus 14 minus f of x, which was x squared plus 8x minus 10. All right, show that and then show the final answer. Again, remember, we can simplify that. -3x to the 4th, negative x squared plus 10x plus 14 minus x squared minus 8x plus 10. That was a 10. All right, collect like terms. So my area is solving the integral from -3 to 4 of my -2x squared plus 2x plus 24 dx. Right? I want to see these. Now, if you do the middle step in your head, that's fine. Just make sure you're careful. But those are the two things I want to see. I want to see what you're subtracting, and then once you've subtracted, what you get. And then you solve that. Now, again, I'm going to solve this algebraically. So I'm going to regraph. I'm going to graph this new function, which I can solve using the fundamental theorem of calculus. So I'm going to regraph that. -2x squared plus 2x plus 24. So I'm going to go back to my graphing calculator. I'm going to clear out what I have. Clear. So -2x squared plus 2x plus 24 was my new function. I'm going to leave the same window I had before. Alright, so there's my graph, -3. Alright, you'll notice -3 is where it intersects. And a lot of times this is what happens, especially with parabolas. The area between the two is this shaded region. So now I'm going to hit second trace. I'm going to shade in. So I'm going to pick 7. I'm going to go from -3 to +4. It'll find that area, which again is a different shape. But it's 114 and a third. And a lot of times they come out 3s because, right, if we take the antiderivative, it would have been x cubed divided by 3. So we do get a lot of thirds in our answers. Alright, so we graph, and again, you should show the graph, so I know that's how the reader solved it. And so -3 to 4, we graph for this function, we found this area, which solves the integration, which was 114 and a third, right, 3 repeating, so the area equals 114 and a third between f of x and g of x, or enclosed by f of x. Alright, that's the area. So again, this area is exactly the same as this area. Alright, it's just a different shape. But what's unique about this theorem is that we regraph it so that I can use the fundamental theorem of calculus, and the two areas are a different shape but the same size. So they're equivalent. Alright, we'll stop there. The last thing from this is average values of a function.